So we were talking about the different types of milling. So we have seen here, this is the first type in peripheral milling. In peripheral milling, first, in order to account for the approach distance, okay, so we have the time required to mill a workpiece of length L must account for the approach distance as we have seen in the previous case to fully engage the cutter. So first we will consider the case of slab milling. To determine the time to perform a slab milling operation, the approach distance A to reach full cutter depth is given by the following relation. Okay, so in case of peripheral milling, the approach distance is radical depth of the cut times big D minus small d, where big D represents the diameter of the milling cutter and small d is the depth of the cut. So what do we mean by this? If you go back to the figure, as you can see here, you have a certain first approach before reaching the position where you really start to cut. Because look, in order to have milling operation, you should have your center. The center position should be here. Should be just at the beginning of your work part. So the actual position where you can consider that the milling operation will start is this one, where you have that your center, the center of your cutter is just above the starting of the work part. This is why you should move your cutter a certain position in your work part in order to be ready to start the operation. This is the approach distance A. Okay, and as you can see, A will be geometrically related to the diameter of the cutter and the depth of the cut by the relation given. Okay, and of course, after accounting for the allowance approach distance, then you should find what is the value of L. L is the length of your work part. So, of course, in case you want to perform the milling operation over the whole work part, then you will consider L plus A as the total distance. Okay. So now we can compute in this way what is the machining milling time. The machining milling time is determined as L plus A over the feed rate. Now, what will vary from one milling operation to the other is this term. So we will try to find how the approach distance will vary between a certain milling type and another. Okay? No. So for case of peripheral milling, this is the formula. Now we will consider face milling. In case of face milling, also we have several relative positions between the work part and the cutter. Okay, so let us see in the picture two possible positions for face milling. So here, for example, you have, in case of face milling, you have a face milling showing approach, and in case of first, when the cutter is centered over the workpiece, and when the cutter is offset to one side over the work. Okay, so in this case, sometimes we want to perform, let's say, the cut here. Let's say you want to produce, for example, in case you are doing a certain milling approach, you can just put the cutter centered on the face, or you can just take it at one side from the work part. And in this case, the approach distance will be different. Okay, so for example, here, if you consider this figure, okay, you should take into consideration several factors. You should take into consideration what is the width of your work part. Okay, you should take also into consideration what is the diameter of your cutter. Okay, sometimes you can have, for example, several cases to take into account. You can have W smaller than D. You can have W larger than D. So depending on the case, the formula of A will be different. Okay, so for example, here in this formula, as you can see, it's clear that it's applicable for D larger than W. because if D is smaller than W, you will have radical of a negative number. Okay, so the first scenario is in case D is larger than W, as you can see here in figure A. Okay, so in this case, when you have the cutter centered over the workpiece, then the approach distance to calculate will be equal to 0.5 times D minus radical D square minus omega square. Okay, and in particular, when D equals to omega, what will happen? If D equals to the width, then this term will cancel out, and A will be equal to 0.5 D. And this is very logical, because if you have just the width equal to the diameter, then if you draw the figure, so just the width is just equal to D, then what will happen is that you need to, in order to reach the full diameter of the cutter at the first end of your work part, you should just move your cutter a distance equal to the radius, which is D over 2. So in particular, when W is equal to D, you will end up with A equals to 0.5 D. And in case D is larger than W, then the distance will be computed by the following relation. Okay? Now, in case D is smaller than W, then we need another formula. Okay? So what will happen if D is smaller than W is that we will do a slot in the work part. Okay? So imagine in the figure here that this is your work part. So your work part is larger than the cutter, like this. So what will happen then? You will, when you move your cutter through the work part, you will produce a certain slot in it. Okay, and therefore also in this case, what is the approaching distance? Of course, also it's D over 2. And in case D is smaller or equal to omega, the approach distance is D over 2. In case D is larger than omega, it's given by the relation we have seen to pass. And if D is smaller than omega, then what will happen that we will create a certain, so we will remove material. We will create a slot inside the material. Okay, so in this case, a slot is cut into the material, and then we can determine in all cases, okay, we can determine the machining time by L plus A over F. Now, the second type of cases is when the cutter is offset to one side of the work. So if you have the cutter offset to one side of the work, then you have a different formula also for the approach distance. So as you can see here, this is the case of the second figure, which is, if you want, similar to the case we have seen in the first, in the peripheral milling. So here, if you know the value of the width, W, okay, and you know the value of your diameter, D, and you want to determine what will be the approach distance, then in this case, you will relate A to D and the depth you are cutting inside your work part. So the approach distance will be function of this. So this scenario is as peripheral milling. So in peripheral milling, you want to remove from just one side. Okay, so you have to account. You should know what is the depth you want to remove, and you should know the diameter of your cutters. Then you can determine the approach distance A. So the approach distance A then can be calculated in this case by the following formula. It's equal to a radical of W times D minus W. Okay, and in all cases, the machining time will be calculated as L plus A over F1. Okay, so in all of these milling scenarios, Tm will represent the time of the cutter, T's are engaged in the work, making chips, The approach and over travel distances are usually added at the beginning and end of each cut to allow access to the work for loading and unloading. And in addition to the machining time, okay, we will see that we should add the time, because you know that you should bring your cutter, you should approach, and even before A, you have a certain time to handle your cutter and to approach it towards, and before getting it ready to be used, you should have a certain handling time. And after finishing the operation, you will unload the system. So also this will require a certain time. This is why we will see after that the total time to account for is, in addition to the machining time, we should add the loading and unloading times. So these times will be added to the actual duration of the cutter feed motion. So this is why the total time will be larger than the machining time here. Okay, and we'll see in details in future chapters how to account for these times. Any question on this? So these are the main relations of chapter 18. Next time we will do some problems together on chapter 18. Okay? Any question before we start? Thank you. See you next time. Bye bye.